In this video, we'll learn how to model distributed material nonlinearity in frame elements in SAP 2000. We'll analyze the behavior of a slender reinforced concrete cantilever column. Our main focus will be on how the material's nonlinear behavior influences second-order effects. Here, we'll compare the second-order effects obtained with two different reinforcement solutions for the same column. We have a cantilever column with the following loads applied at the top joint: 250 kilonewtons of vertical load in the dead load pattern, 95 kilonewtons of vertical load, and horizontal loads of 10 and 5 kilonewtons in the live load pattern. We can see that the column is slender, with its weaker axis aligned with the 10 kilonewtons load direction. The column's cross-section is 65 by 50 centimeters, and its length is 12 meters. Let's review the properties of this cross-section. C3037 concrete. A500 steel reinforcement. 16 longitudinal rebars with a diameter of 20 millimeters. As mentioned, our main goal is to compare second-order effects for two different reinforcement solutions. Thus, we have a second cross-section that only differs by having 16 millimeters rebars instead of 20 millimeters. Next, let's examine and edit the nonlinear properties of the materials used in the column's cross-section. We'll start with the reinforcement material. We'll accept the parametric definition of its stress-strain curve, with a yield stress of 500 megapascals and an ultimate strength of 550 megapascals. Now, let's edit the concrete properties. Here is the parametric stress-strain curve for unconfined concrete. We'll keep this behavior but set the concrete's tensile strength to 0. To do that, we switch its stress-strain curve to user-defined and eliminate the tensile stress. We'll increase the strain for that point, just to make it more visually apparent in the graph. And then we'll remove line 10, which is now redundant. We can see the updated curve with no tensile resistance. We accept these changes and move on to our ultimate limit state load combination. Because we want to model the column's nonlinear behavior, we must convert this combination into a nonlinear analysis that applies these loads and scale factors. By clicking here, the program automatically creates the relevant analysis, and its results will feed directly into this load combination. Note that we could do the same operation for multiple combinations in one go, which is often the common scenario. Now, let's look at the load case that has been generated when we converted the load combination. We see the applied loads in a nonlinear analysis that includes P-delta effects. Next, we define the plastic hinge concept that we want to use for distributing plasticity along the column. We add a new plastic hinge called fiber PM2M3. We'll leave default from section so that SAP 2000 automatically creates a fiber layout based on the assigned cross-section. If desired, we could control this auto-discretization into fibers by assigning section designer cross-sections to the frame objects. Now we specify a hinge length of 1, corresponding to 100% of the frame object. However, when we apply distributed plastic hinges, SAP 2000 automatically calculates the tributary length for each hinge, regardless of this value. We'll confirm that later. We accept, and we're ready to assign this hinge concept to our column. We choose the equal spacing option to distribute the hinges evenly. We specify 10 hinges along the column, using the fiber hinge we just created. We apply, then switch off the extruded view to observe the newly assigned hinges. Here we see the first hinge at 5% of the frame length, that is, 0.6 meters. Followed by evenly spaced hinges at increments of 10%, each 1.2 meters apart. We also asked SAP2000 to auto-mesh this frame element, centering finite elements at each fiber hinge. Here, the 0.2 value is irrelevant because we're telling SAP2000 to adopt the hinges lengths directly. Now let's examine the automatically generated hinges to confirm everything is correct. We turn on Show Generated Props to see the 10 generated hinges. For example, let's look at hinge 1H11. We see that the hinge length value has adjusted to match the tributary length of 1.2 meters between hinges. We have a relative value of 0.1, which, when multiplied by the 12 meters length of the column, results in exactly 1.2 meters. We can also check the steel and concrete fibers that have been created for this cross-section. We see multiple steel fibers of 3.14 square centimeters each, matching the cross-sectional area of the 20 mm rebars, as well as the C3037 concrete fibers. We're now ready to run the analysis. The results are available now. Let's check the M3 moment diagram from this non-linear analysis. By the color scale, we see that the maximum moment is around 250 kilonewtons meter. Now we'll simply change the column's cross-section properties to use 16 mm rebars instead of 20 mm. We can run the model again and check the difference in flexural moments. Now approaching 340 kilonewtons meter. So, we can conclude that the reduced stiffness, caused by lower reinforcement, leads to significantly higher second-order moments. Next, let's explore the nonlinear behavior across the plastic hinges and their fibers. If we want to plot force displacement, moment rotation, or stress-strain curves, we need to store multiple states at different load increments. We'll request 50 states and run the analysis again. First, we confirm that at the final step, step 50, we reach the same flexural moment as before. Now, let's examine the hinge results. We look at the behavior of the bottom hinge, 1H1, and see its moment rotation curve. Finally, let's see how each fiber responds. Here is fiber 1, which corresponds to a rebar. Now we check a concrete fiber, say fiber 19, in the top left corner. This one is under high compression but still well below its strength limit. We return to the rebar fibers and note that the rebar in the opposite corner is nearly at yield stress. With that, we conclude this brief example, showing how easily we can account for distributed material nonlinearity in frame elements in SAP 2000.